All right, for this lesson, we're going to take a look at how to solve non-right angle triangles using what is called the sine law. Now, it won't work for all right angle triangles, but we'll get into the circumstances where you can use this. So in order to do this, first thing we need to make sure that we know how to solve angles and side lengths given a right angle triangle, like we did in grade 10. So if it wants me to solve what this angle is, then based on this angle, I know the opposite side length, I know the hypotenuse. The only trig ratio that uses opposite and hypotenuse is sine. So I can say that sine of x degrees is equal to 8 over 14. If I know what the ratio is, then I can always solve what the angle is using sine to the negative 1. And in this case, it's going to give me 35 degrees. At the same rate, if I know the angle, then I know what the ratio is, and I know one of the side lengths, I can use that to solve another side length. So I know the angle, I know what the adjacent side length is, and I'm trying to solve the hypotenuse. The only trig ratio that has adjacent and hypotenuse is going to be cos. So if I know that cos of, in this case, 40 degrees is equal to my adjacent of 19 over my hypotenuse, which is represented by x, then I can rearrange my formula to say that x would be the same as 19 divided by cos of 40 degrees, which is going to be approximately 25. Now, if I relate that to a non-right angle triangle, in this case, it's going to work because I gave you the measurements that would make these right angle triangles, which later on in this unit I will not. But I can use this information in order to derive a way to solve it. So if it wants to know what the length of B to C is, it wants to know that entire length. How do we do that from this non-right angle triangle? We created an altitude, which we call height here, by taking the point of A, drawing it straight down perpendicular to BC, and then creating a new point that doesn't exist in the original triangle of D. From there, I'm going to state that I have two separate parts that exist here and that exist here that are side lengths of the right angle triangles. And in this case, I'm just going to go ahead and call them X and Y. So from one of the right angle triangles, I know the acute angle, I know the hypotenuse, and I'm trying to solve what the opposite side length is that I called x. Using the exact same principle we did in the last case, if it's opposite and hypotenuse, it's going to be sine. And if sine of 20 degrees is equal to x over a hypotenuse of 12.5, then to get x by itself, x is going to equal 12.5 times sine of 20 degrees. Even though it wants my final answer as 2 decimal places, I'm going to go a little bit beyond that just to make sure I don't do a rounding error at the end. I'm going to call x 4.275 centimeters approximately. Now I can't jump right to solving my y value because I don't know any of the measurements in the right triangle ACD, but I do know that they have a shared side length here that I can solve for. Now when I'm solving for this, I'm not going to use the x1 that I just solved for in case I made some sort of rounding error. I'm going to use the exact value it gave me. So I know the angle, I know the hypotenuse, and in this case I'm trying to solve the adjacent. To solve for my height, I'm going to use cos. And my height is going to equal my hypotenuse, 12.5, times cos of the same 20 degrees. And my height is going to be approximately 11.746 centimeters. Once again, rounding past what I'm requiring for the final answer. And at this point, I'm going to use my other acute angle of 55 degrees or 35 degrees. Doesn't actually matter which one. In this case, I'll just use 55. And I'm going to use this adjacent in order to solve for my opposite, which is y. Adjacent and opposite is only created with tan. So tan of 55 is going to equal my opposite, which is represented by y in this case, divided by my adjacent, which I said is approximately 11.746. Which means that y is going to equal 11.746 multiplied by tan of 55 degrees. My y is going to be approximately 16.775 centimeters. And last but not least, I'm going to state that BC is equal to x plus y, or 4.275 plus 16.775. The length of BC is equal to 21.05 centimeters. Now, that did get me to the point that I needed, but it was a very long process to get there. Sine law is going to speed up that process, and it's also going to help us when we do not use, or when we don't have the measurements for the right angle triangles. So now we need to figure out a different way to label triangles based on assuming they're not right angle triangles. And the way that we do that is we do it by the angle and the opposite side length. We don't use adjacent and hypotenuse anymore because there is no hypotenuse when it isn't a right angle triangle. And if there is no hypotenuse, then both of the side lengths that are touching the angle are adjacent. So neither of those terms make sense for us. But the opposite side length is always the opposite side length. It's the whatever side length isn't touching it. So all we can do is label triangles based on the angle and the side opposite. So if I said that this is angle A, then this is going to be side length A. If I said that this is angle C, then this is going to be side length C. And I always use a little line over top of it because C, capital C and lowercase c look exactly the same. So I just put a little line over it just to indicate that it's a lowercase. You don't have to do that. And if this is angle B, this is side length B. Now, this is on your formula sheet. In every triangle, whether it's a right angle triangle or not, the ratio between the sine of the angle and the side length opposite, or its reciprocal, will be the same for every single angle and side length that exists in here. If I took side length A divided by sine A, it's the exact same as side length C divided by sine C, side length B divided by sine B, or its reciprocals. How does that work? Well, if I take a non-right angle triangle, just like the one that we did in the first example, and I labeled that this side was B because it's opposite of my angle B. I created that same altitude going from C directly down to go perpendicular. Then in this case, I can say that sine of angle A would be the side length opposite CD divided by the hypotenuse of this right angle triangle here of AC. But we know that AC is actually side length B. It is the side that is opposite angle B in the non-right angle triangle, the bigger triangle. If that's true, then when I get CD by itself, then I'm going to multiply B into both sides and say that it's going to be B times sine of angle A. If I flipped the triangle, then suddenly this is side length A. I still have that verticality or height or altitude, depending on the term you want to use, of CD. And I can say that sine of angle B on the other side of the triangle would be the same as the opposite, which is still CD, divided by the hypotenuse of BC, but we know that BC is actually side length A in the non-right angle triangle. So CD in this case would also be A times sine of B. Now, because they're both CD in the exact same triangle, then B sine A has to be the same as A sine B. And depending on if I divide both sides by A and B, then I'm going to get this ratio. If I divide both sides by sine A and sine B to leave the variables on the top, I get this ratio. If I rotated the triangle and then created an altitude at B instead of at C, I could prove the exact same thing works where the ratio of A over sine A is the same as C over sine C, which means that this works for any side on a non-right angle triangle.